3 decades, the NASA Ames Vertical Motion Simulator has provided the shuttle program with engineering studies and pilot training for the shuttle landing and rollout phase. Since April 1980, the VMS has been an important developmental tool for the shuttle program. Unlike most new aircraft programs with extensive flight testing, only 5 free flight landings were performed as part of the approach and landing tests for the first shuttle mission. To date, the shuttle program has 130 successful mission landings. Due to the low number of flights, the VMS has played a major role in what would normally be part of the flight testing. The VMS has been used as a testbed to determine the effects of various engineering and operational changes for pilots in the loop handling quality. The VMS is a unique, high-fidelity, large-amplitude, 6 degrees of freedom motion flight simulator. The large motion envelope of the VMS simulates the touchdown and rollout motion cueing of the actual shuttle landing. The system architecture in the VMS is flexible by design. It allows integration of external software modules and unique vehicle-specific hardware. This has enabled the shuttle program to use the VMS to develop, test, and evaluate numerous changes that have improved the safety and operation of the orbiter. Early use of the VMS to investigate and address handling quality issues played a major role in the use of the VMS for training. The first VMS simulation investigated a pilot-induced oscillation, or PIO, that the orbiter encountered during approach and landing tests. Prior to use of the VMS, the Ames Flight Simulator for Advanced Aircraft was used for the PIO testing but did not provide the vertical motion cueing with enough fidelity to recreate the PIO. When the VMS became operational in 1980, this test was repeated and the VMS was able to recreate the vertical cueing necessary to reproduce the PIO. After that, the VMS has been used extensively by the shuttle program for engineering studies as well as pilot training. Landing and rollout is defined as the phase of flight from Mach 0.95 to touchdown, where the shuttle commander manually flies the orbiter. This is a demanding task in many ways. First, the flight crew have been in microgravity conditions for some length of time and are adapting from extended weightlessness to Earth's gravity during approach and landing. Second, the Space Shuttle's flight control system is a 3-axis rate command system designed to deal with changing aerodynamics during the entry phase. This requires years of training by pilots to perfect the precision, small amplitude, low gain input flying necessary to perform a safe landing. Lastly, the Space Shuttle's rapidly descending approach and landing profile is unpowered, so it must be done correctly on the first attempt, unlike any other aircraft. For these reasons, the training on the VMS simulator is critical to the astronauts. The phase of flight from Mach 0.95 to touchdown encompasses subsonic terminal area energy management, or TAME, as well as approach and landing guidance. TAME has 4 flight phases: S-turn, acquisition, heading alignment, and pre-final. Approach and landing guidance has 5 segments: trajectory capture, outer glide slope, shallow glide slope, final flare, and touchdown and rollout. Orbiter landing simulators provide simulations of the heading alignment phase, also referred to as a heading alignment cone, to touchdown. The orbiter will intercept the heading alignment cone and spiral down until it is lined up to begin the approach and landing phase. The approach and landing phase begins at 10,000 feet at a glide slope of 20 degrees for a lightweight orbiter. At approximately 2,000 feet, the orbiter will begin to transition to a 1.5 degree glide slope until the final flare and touchdown. The main gear is targeted for 2,500 feet down the runway, traveling at a velocity of 195 knots. Shortly after touchdown of the main gear, the pilot will deploy drag chute. At a velocity of 185 knots, the commander will derotate at 1.5 degrees per second until the nose gear touches down. Braking starts after the orbiter has decelerated below 120 knots. The pilot will jettison the chute at 60 knots as the commander brings the vehicle to a stop. Approximately 27 updates have been incorporated into the shuttle flight software and hardware systems over the past 30 years. The VMS has been used to conduct more than 80 engineering studies that have led to more than 20 shuttle flight rule changes. The most recent engineering study was the crew evaluation of the modified braking procedures. It resulted in a flight rule change to the braking procedures on the Edwards Air Force Base temporary runway. Some significant models incorporated into the VMS include studying various drag chute sizes to see which would be adequate for rollout operations, evaluating crosswinds for all weights, which resulted in helping define the orbiter's limits, studying the heads-up display derotation cues, studying the main and nose gear drag, tire compression, side energy, side loads, and normal loads, investigating the carbon-carbon brake energies encountered during worst-case tail landings, evaluating 3 equivalent airspeeds for use in a redundant beep trim software modification, allowing minimum degradation of derotation handling qualities and tire loading. The continuous reviews of the VMS simulation results have led to systematic improvements to the shuttle's landing and rollout simulation. These improvements have led to better training results and improved safety and operation of the orbiter. Landing and rollout training on the VMS has been an integral part of the shuttle program. Simulation scenarios are developed for various environmental conditions, emergency landings, as well as system failures including blown tires and chute malfunctions. Every pilot who has flown the shuttle has trained on the VMS. More than 65,000 landing and rollout training and engineering runs have been completed. Other than on the actual orbiter, the VMS is the only place where a shuttle pilot can feel what it's like to land the vehicle. Experienced shuttle commanders have stated that the VMS is the most accurate representation of a shuttle landing and rollout.